Good afternoon, everyone. First of all, I would like to thank the organizers for giving me this opportunity to present my work here. So today I will be talking about percolation of aligned and overlapping shape anisotropic objects on lattices. This work is done under the guidance of Dr. Shashi Devan, Cochin University of Science and Technology. So outline of my talk is as follows. First, we have an introduction to percolation. Then we discuss percolation of aligned overlapping anisotropic shapes on lattices, semi-continuum models, and finally conclusions. So we begin with percolation. It is a model to study the connectivity of random and disordered media. Percolation phase transition is characterized by emergence of a spanning cluster in the system. The model is classified into lattice percolation and continuum percolation. In lattice percolation, we can have lattice site model or a lattice bound model. Here, sites are occupied randomly with some probability P. In case of continuum percolation, we have objects of arbitrary shape dropped onto a plane with a specific number density. So the control parameters in the model are occupation probability for lattice and number density for continuum. So in percolation model, we have transition point known as percolation threshold. It is a critical occupation probability or critical number density at which the transition occurs from disconnected state to a connected state. So we are studying percolation of extended overlapping shapes on lattices. These extended shapes can be discs, squares, rectangles, etc. And this interesting thing about these models is that they interpolate between lattice and continuum. Main features of the model are multi-site occupancy and multiple occupancy. So why we are interested in studying a system of aligned overlapping anisotropic shapes on lattices? The first question we have in our mind is how does anisotropic shape show discrete to continuum transition? We have a discrete to continuum transition observed in the case of symmetric shapes like discs, squares, etc. But in the case of anisotropic shapes, how does such a transition occur? Another aspect of our study is that in 2D continuum model of aligned rectangles, percolation threshold is independent of aspect ratio. But in the case of continuum models, we can see that there is affine symmetry present in the system. That is, if we consider a system of aligned overlapping squares or overlapping discs, we can see that if we perform an affine stretch of the system in the vertical direction, the percolation properties or the connectivity properties will remain the same. But lattices do not have such a symmetry under scaling. So the peculiar properties will arise in lattice systems. So we are interested in studying that models. Moreover, these aligned overlapping anisotropic shapes, especially rectangles, are useful in the study of transport properties in porous media. We have a typical example of anisotropic shapes, that is rectangles on lattices. We are considering K1 by K2 rectangles in an L by L system, a 2D square lattice. So we are looking for connected path of rectangles in the vertical direction which form that spanning cluster. Here we use the same terminology from continuum percolation, that is phi or density of occupied sites is calculated by 1 minus exponential minus eta, where eta is the areal density. Here are two typical configurations of aligned rectangles. First one is non-percolating, while the second one is percolating. We have an analytic approximation method to study these models, that are excluded volume theory. This excluded volume theory is actually proposed for continuum system, but later it was extended to lattice systems. And this theory states that the product of number density of basic percolating units and average excluded volume is an invariant quantity for similar systems at criticality. Here similar systems are used in the sense that they must have the same orientation distribution. So we are calculating phi c or percolation threshold using this. And here we can see that excluded area or volume is a connectedness factor in lattice system, but it is an area or volume for continuum systems. Now, using this theory, we are calculating phi c for aligned rectangle system, and the theory predicts that for width k2 equal to 1, threshold is a monotonically decreasing function of k1. For width k2 equal to 2, threshold is a constant. For width 3, threshold is monotonically increasing. That is, for aligned rectangles of width 2, threshold is independent of its length. And the theory predicts similar results for other lattices, that is like parallelograms on triangular lattices. For width K2 equal to 1, threshold is a constant. For width 2, threshold is monotonically increasing. These are the results for various shapes, lattices, and dimensions. In all cases, limiting values are finite. There are some other interesting predictions of the theory, that is, length independence of threshold can be extended to higher dimensions, for example, in 3 dimensions. And we can define a parameter S, that is, fraction of rectangles having mixed orientation. S equal to 1 is for fully aligned case, and S equal to 0 for isotropic cases. We can derive an S-dependent expression for excluded volume, and using this, we can see that for S less than 1 and for large K1, phi c always monotonically decreases. That is, completely aligned cases are always unique. Interesting trends are observed only for S equal to 1 cases. These are the simulation studies. So we calculate threshold for increasing values of K1 for a particular width K2. Width-dependent trends in threshold are observed. So we can see that the theory and simulation results are in agreement with each other. And some related findings are the model of aligned rectangle show isotropy in threshold, that is horizontal and vertical threshold are the same. The model belongs to standard percolation universality class. As shown in the figure, we have plot for data collapse as well as plot for obtaining the exponent beta by nu. And the increase of rectangle alignment or S parameter leads to increase of threshold. Now we have the continual limit of lattice model. So we calculate the limiting value, and from previous studies for symmetric shapes, we have a result that continuum percolation of aligned object can be regarded as a limit of corresponding discrete model. And here we calculate a special limiting case, that is K1 tending to infinity with K2 held as a constant. This limit is finite and is different from the continuum threshold of rectangles. That is, lattice spacing is tending to 0 in only one direction. This appears as a special kind of percolation model, which is a semi-continuum model. So we have overlapping objects in lanes or semi-continuum models. Here, objects can have continuous x coordinates with discrete y coordinates. That is, object width appears as integer multiples of lane width. There is no restriction on overlapping in the x direction, and we can see in figure that two configurations are the first one is non-percolating while the second one is percolating in the vertical direction. So the theory predictions can be compared. Here we can see that for semi-continuum model of rectangle, width-dependent phenomena is observed. That is, threshold is independent of length K1 for a particular width K2. Similarly, a comparison for overlapping squares are also done. For lattice model, there is a non-monotonic behavior. For semi-continuum model, there is a monotonic increase. So the conclusions are lattice version of theory, excluded volume theory yield predictions of higher accuracy. Shape anisotropy leads to width-dependent trends in percolation threshold of systems. Similar trends can be obtained for anisotropic shapes on other lattices and dimensions. Width-dependent trends are unique for S equal to 1 cases. For shape anisotropic objects, special limiting case appears as a semi-continuum model. Semi-continuum models show a width-dependent phenomena. With that, thank you.
Time for quick questions. Okay, if there is no questions, let us thank the speaker.